Welcome, everyone, and thank you for joining us today. My name is Paul Donahue, and I will be your host. We ask that you please keep your device muted during the session, and if you have questions, please direct them to me via the chat function. We'll do our best to answer questions at the end and to follow up with any unanswered questions via email. As I think you know, these Tech Talks have been designed to provide straightforward insights into radio frequency components, the related technology, and the extra design and engineering value that is added by a custom manufacturer such as Quantic TRM. To begin today's session, I am once again pleased to introduce Quantic TRM's Chief Technology Officer, Shaun Moore. The author of 2 U.S. patents and a number of white papers and technical articles on passive microwave technologies, Shaun has been with Quantic TRM since the late 90s, and his passion for the job and for solving problems has only increased over the years, especially when it comes to resolving our customers' design and engineering challenges. So welcome, Shaun. Can you share an overview of today's topic and your objectives for the session?
Yes, thank you, Paul. So today, basically what we'd like to talk about here really are some of the fundamental things that are important for designing parts for spacecraft. What we're going to focus on here between this presentation and our next presentation, since there are enough sort of details that need to be considered, this is going to be a part A and a part B going through with really what we're looking for. But really, there are a few things that are critical for being successful in designing parts for spacecraft. I think really what we're going to talk about today really are some unique failure modes, or things that typically do not happen when you're building terrestrial parts, or parts that are going to be here being used pretty much at sea level. So there's a series of failure modes that tend to happen either in a vacuum or near vacuum, and that's really where we're going to focus today. Then we're going to go through a couple of applications as far as where our parts are used on spacecraft, and then go through some TRM differentiators, and then we'll sum it up.
Well, thanks, Shaun. That sounds good. And to get started, earlier I mentioned that a lot of what you do is dependent upon a user's or the end user's environment profile, and that has a big impact on designing parts for space applications. Could you tell us a little more about that?
Sure. So really, I think the thing that we're going to focus on today are things for requirements really for designing parts that will operate in a vacuum. And I think it's really important to understand what's important about operating in a vacuum, and really what does the absence of air do for the operation of our parts. So really what we're going to talk about today really are some failure modes, and as well as some other things that we need to be cognizant of as we're designing parts. The first of which is something called multi-paction, and we're going to talk about what a multi-pactor is, how it affects parts, and how we actually have to design around those sort of limitations of the multi-pactor failure mechanism. Another thing that's also very important to bring up is heat. When we're designing parts for spacecraft, you have to realize that heat cannot radiate because there's nothing to radiate to. Therefore, all heat and thermal buildup must be conducted away from the components for thermal management. Also, as we are looking at having parts, being on a launch vehicle, there is a time when the parts would go from full pressure to a near vacuum and then into a total vacuum. So there are other failure modes that can happen, such as corona, which require a little bit of air in order for that failure mode to happen. But there's something called a critical pressure, which happens during launch, that creates a very sensitive area that we need to be very cognizant of as we're designing these parts.
Okay, so maybe we could start by defining exactly what multi-paction is.
That's a great place to start, Paul. So multi-paction is a failure mechanism that has to do with free electrons. And it's going to sound a little bit complicated, but kind of stick with me here, and we'll go through this. So multi-paction occurs when an electron leaves a plate or conductor and travels across space and then arrives at the ground leg or another conductor. And what's important about the multi-impactor effect is the electron has to be able to jump the gap without intersecting any other molecules. So the electron has to make a jump across free space from one electrode to another. That's part one of what defines a multi-impactor failure. What happens then is that as that free electron jumps that gap, the field that induced the electron to jump across the gap to begin with reverses direction. And it reverses direction at the same time that free electron arrives at the other electrode. What happens then is that if you picture a ball or something dropping onto dirt, a little dust cloud comes up. That little dust cloud, in essence, in my analogy, is other electrons being released from the secondary plate that are reflected back towards the first plate. Now, since the field has reversed, they're now being accelerated back the other way. So what happens then is we have an exponential growth in electrons traveling back and forth between these plates. That is the multi-impactor mode as far as to how that actually happens. So it is a resonant condition where free electrons are, due to the field, the electric field that is available, are accelerated across the gap. They do not collide with anything, so it is a clear travel of electron from one electrode to another. When it arrives, the field reverses. The electron's impact on the secondary plate releases more electrons, and then they get forced back the other way. So it becomes this resonant condition of these electrons going back and forth between two plates.
Okay, so you were right. That is interesting. So when the electrons jump the gap, how does it affect the system?
Okay, so really there are multiple effects on the system. At a very small level, and I think I want to point out here that multi-impacting can happen at very low voltages. Typically, it can happen as low as 25 volts, which is something that you really don't think about voltages that low having this sort of a voltage breakdown problem with voltages that are that low. Typically, we think of voltage breakdowns happening at several hundred volts. Multi-impacting can happen at very low voltages. Like I said, it can happen as low as 25 volts. What effect that has on the system? If it is a low voltage breakdown, if you think about the electron jumping back and forth between these two plates, if you think about what thermal noise is to an electrical system, the thermal noise or your KTB type noise, which is basically just noise that happens because electrons are moving on a plate. This sort of active movement of electrons between two plates significantly increases that thermal noise. So what happens typically when this multi-impactor happens is that the signal to noise ratio of the system gets so bad that you lose the signal. And that is, at one level of a multi-impactor. So basically you can make a system non-functional because the system noise has increased so significantly that you can no longer discern the signal that you're trying to trace. When the multi-impacting gets worse and the energy levels get a little bit higher, you can start to see actual component damage and permanent failure of those components due to other damage that happens due to having this significant amount of voltage hitting and colliding with plates. In that case, you start getting damage very much like you'd like to begin to see with more like a corona type breakdown, where parts are actually physically damaged. I think it's important to mention out here, again, that multi-impactor effect is a resonant breakdown condition. You have to have several things that happen in order to actually have the multi-impactor effect happen, of how these electrons jumping back and forth between two electrodes, and then having that sort of sustained resonant condition happening.
Okay, so you mentioned that several things have to happen. Maybe could you just tell us, how does multi-impacting actually happen?
Sure. So both multi-impacting and corona are different forms of voltage breakdown. And I think Corona is something that I think that we experience. It's and that's something that we can understand. There's just a dielectric breakdown, and then energy jumps the gap. Um, the the multi-paction breakdown, though, is actually a very different mechanism. Like I said, it is a resonant condition, which can happen at fairly low voltages. Because the mechanisms are very different, you have to treat them and you have to analyze them independently, although the failure modes may seem to be similar on the face of it, and in actuality, they are quite different. So that's why we have to, carefully consider both failure modes for parts for spacecraft.
Okay, so you mentioned that the multi-paction mechanism is different. Maybe you could explain that a little bit more?
Yeah, and I think what's important here when we talk about a resonant condition, there is a short list of things that must occur in order for multi-paction to happen. If any of these conditions change, then you can change the point either at which multi-paction will happen, whether it be frequency, power, or voltage, or whether or not multi-paction can even happen at all. So first thing that we need a vacuum or a near vacuum. By that, what I mean is that we have to have a free path for the electron jump from one electrode to another without hitting another molecule. That only happens in a vacuum or someplace where we're in a near vacuum, where there can be free electrons traveling back and forth without colliding with something else. That's critical because as soon as an electron collides with another molecule, by definition is no longer multi-pactor failure, then we're going into a corona or an ionization type failure. Second thing is the gap distance, or the time that it takes for that electron to travel from one electrode to the other, has to be a resonant condition along with the frequency of the field. The same time that it takes for that electron to jump from one electrode to the other has to be the same time that it takes for that field to reverse directions, therefore creating that resonant condition of this energy going back and forth. You also need to have enough voltage to free a free electron without having enough energy on the plates to dislodge an electron. Then this condition will not happen. Something else I think it's important also is the shape of the electrodes. Electrons do not always travel in a straight line. They will follow the electric field, and electric fields do have various shapes depending on the shape of the conductor that they are between. Parallel plates will have one shape. A rod will have another shape coming off of it. A coaxial shape will have yet another different type of field that gets built up there. So the shape of the field also affects the mean path length of that electron, which is how long it takes to jump that gap. And again, the frequency of the voltage has to reverse exactly when that electron hits the other side. So the time that it takes to get across there and the time that it takes for that field to reverse all have to kind of align themselves so that this condition can happen. And like I said, the result of that is that it is a resonant condition. What's important here is by changing any one of these parameters, it may be possible to avoid multi-pacting. And I think the avoiding multi-pacting is what TRM does when we design parts for spacecraft. We just don't try to push it a little out of band as far as having the multi-pactor happen. We actually work very hard to make sure that multi-paction cannot happen in a very significant band around the band of operation for our parts.
So do we always have to have two surfaces for multi-paction to take place, or can it occur on a single surface?
It can occur on a single surface, and I think this is something I think that most people don't realize. The two-surface multi-pactor, which is the one that I just discussed, is actually the easier one to envision. A one-surface multi-pactor is something that is much more difficult to imagine. A single-surface multi-pactor, though, happens when an electron leaves a surface. And for this over here, it can be a metal surface, although more than typically it is a dielectric surface, any place where a free charge can collect. And that the electric field causes that free electron to jump up into space. As that electron jumps up into space, it has just enough energy to get it launching. And just as it's losing energy going away, the field reverses and pulls that electron back down to that surface. Again, that electron colliding on that surface creates a little dust cloud, more electrons are released, and the process repeats and repeats and repeats. So the same effect of having this cascaded electron collisions on that surface will raise the thermal noise on that dielectric, and the same negative effects for the system do happen. So again, this is a case that needs to be careful consideration when we're mitigating from multi-factor. It's not just a gap to gap to gap breakdown failure. It can actually be if you have a single dielectric hanging above a conductor with space on either side of it that allows for this sort of resonant condition to happen. That a single surface multi-factor can be just as problematic as a two surface multi-factor going through and actually handling that.
So what can we conclude from all of this then?
So basically, what we'll conclude here is that multi-packing is a fairly serious condition that we have to make sure that we analyze and make sure that we design out of. I think also remember that multi-packing, in order to occur, has to be in a vacuum or a near vacuum. That is, the electron has to have a free path going from either one surface to the other, or leaving a surface, going up into space, and then coming back without colliding with another molecule. Also, the fact that multi-packing is a resonant condition, which means that the field has to reserve at the time that the electron gets to its destination, allowing the sort of resonant, catastrophic sort of a cascading of happening. And I think what's important to mention here also is if you understand the multi-packing effect, you can design parts so that the multi-packing mechanism cannot happen. And I think that I can't stress that enough. And it's very important when you're designing parts for spacecraft that you design the parts to avoid these sorts of gaps, as well as gaps in materials that allow for this resonant condition to happen.
Okay, so you had mentioned corona a couple of times earlier. Can you define that?
Sure. Now, corona is the other breakdown mechanism that most people actually think about when they think about a gap failure, because this is the condition that happens right here at sea level. Basically, corona is an ionization failure. So what happens here is that the electric field around the component creates a field, and gas that is between across that potential between those two electrodes becomes ionized. By becoming ionized, the components line up to create a lower impedance path between the two electrons. That's what we mean by becoming ionized, is that the conductor loses its a little bit of insulation properties because the molecules will begin to align, and therefore you get a path of lower resistance between two electrodes. When that happens, energy discharges across that gap, and when the energy discharges and goes across that gap, it can cause significant damage. Corona breakdown is almost always a destructive damage. An extreme sort of variety of corona breakdown is lightning, or something along those effects, where you have energy jumping across the gap, and then when that happens, when the energy arrives, it almost always does damage when it arrives.
So what else is corona dependent upon?
So corona is dependent on several things. Like I said, it is a breakdown of gas pressure. So therefore, it is dependent on since the insulating properties of gas are related to pressure. There is a pressure where, let's back up a little bit. The pressure of the gas has a direct effect on how effective that the dielectric strength is. So what happens is as you decrease the gas pressure, the dielectric strength becomes less. And therefore, as you go higher and higher and higher in altitude, the pressure drops. And there is a point where the where the breakdown will become at its minimum. And so we call that critical pressure. Usually if you go up at 50, 60, 70, 80, 90,000 feet, there is a pressure where the gas gets extremely weak. And in that area, you can't have a corona breakdown at a lower voltage than what you would have at sea level. And again, like multi-faction, the gap shape, the frequency, and the actual voltage, depending on where exactly that happens, relative to gas pressure. The other thing also is that the critical pressure and corona are also depending on the type of gas. For example, oxygen will have a very different breakdown than nitrogen or these other sorts of gases. So we have to be careful about how, when we do the analysis, that we do look in there, and depending on what type of gas that we're looking at, as far as how that breakdown mechanism actually happens and where it actually happens. And now at a certain pressure, you will not have enough gas to ionize, and therefore the voltage buildup will start to become again. So in those cases there, and that's where they define sort of a critical pressure. At sea level, the gas has a certain amount of pressure. As you go up in altitude, it becomes less and less and less, and there is a point where the voltage breakdown will hit a minimum. As you continue to decrease the gas pressure, all of a sudden there aren't enough molecules to ionize, and all of a sudden the standoff voltage will begin to go back up again. So there's sort of that place that happens depending on the frequency and the voltage that you have, where you have this sort of a lull in the curve here, where you have to be careful of. Parts for spacecraft have to be launched from sea level into a virtual vacuum. So in that case, all these parts will go through this critical pressure. What's important for parts for spacecraft is whether or not these parts are active during the launch as you're going through this pressure point. Certain parts on the satellite are not active as we're going through this critical pressure point. Other components, for example, if you're on the telemetry system where you're part of the guidance system of the launch vehicle, then it's very important to make sure that you do survive this critical pressure, because the parts will be active during that part of the flight. So it's understanding where these parts are as to whether or not you actually have to go in there and actually pay special attention to corona as part of spacecraft design.
Okay, I think I've got that. So maybe you could outline some of the typical space applications for which TRM customizes components.
Sure. So, we do a lot of parts for, of our spacecraft are based on signal processing as well as communications. A big part of what we do are local oscillator signal distributions for up converters and down converters. And very often spacecrafts will have multiple local oscillators that they want redundancy on, and therefore we will go in and we will have multiple inputs and multiple outputs for these signal distribution networks. We've designed parts that feed phased arrays as part of signal distribution networks. I mentioned just previously launch vehicle telemetry. The launch vehicle needs to know where it is, and there are guidance systems that are associated with that that TRM builds parts for. And again, antenna feed networks as well as mode forming networks are really what we build for spacecraft. In essence, really almost any part that we build for any terrestrial system can be on a spacecraft. What TRM has found is that we see an awful lot of signal distribution work, either for local oscillators or for other mechanisms with all the spacecraft. But there are a lot of parts in the spacecraft that require to move signals around one way or the other.
Okay, and what about sharing some of the innovations or enhancements that TRM typically makes to make all of these things fit the various applications or environment profile?
Sure. So, what we do when we design parts here is we take a very holistic view of the system, and we go through. The first thing we do is we look at potential breakdown issues, both for multi-factor and corona critical pressure. And we actually go in there and we design these parts so that they can't happen. We do things like overlapping dielectrics, eliminating gaps, other void filling things that we do to make sure that these sorts of failure modes really just can't exist. It's part of our culture with what we do here to make sure that we don't get into a situation down the road where we have problems with these. With all of the parts that we have designed to this point, and this point we have over 150 designs flying on spacecraft. We have not had any trouble with the multi-factor or corona in our history, so we're quite proud of that.
Well, I think once again, it's the diligence, the design, and the testing that you've mentioned, and the other innovations that I know really provide you and your people with the greatest amount of satisfaction. And I hope our customers too, I suppose. So we do have time for at least one question here. And you mentioned this a few times, I think, today, but do you need a complete vacuum for multi-paction to happen?
Yeah, no, we don't need a full vacuum. So we it's more likely to happen the better the vacuum is. But what you really need though is you need to have enough of a free path for the electrons to jump between electrodes. Really, I think if you have a gap that is 30 mils or 50 mils across, you need a fairly low pressure to not have any molecules in that gap while we're making that jump. So you don't need a full vacuum, but you need a reasonable vacuum. And I think that's sort of a thing that you just keep in mind as you're going through this. You don't need a perfect vacuum. You can have multi-paction in a partial vacuum as well.
Okay, terrific. Well, thank you, Shaun. Maybe you'd like to just do a quick summary and then we can wrap up.
Yeah, sure. So basically, when we're designing parts for spacecraft, multi-paction and corona breakdown, critical pressure are things that absolutely need to be looked at for every design. It's something that we do here routinely. It's something that we have quite a bit of experience about while we're going ahead and designing these parts. There are many other things that we have to be considerate of as we're designing parts for spacecraft. A lot of material discussions, as well as other reliability issues, and those are things that we're going to talk about next month. So it's not just a one-piece thing here. There's quite a bit going on when you design and build parts for spacecraft.
Excellent. So thank you so much, Shaun, and thank everyone for joining us today. If you are a customer and you would like to ask more questions, you can see the TRM Engineering hotline number on the screen, 888-677-6877. If you're one of our field sales representatives, then you know that you can call us anytime, and a lot of this information will be available through the rep portal, and of course you can work with your CAMs. And in case it's helpful for anyone else that would like to stay tuned for part 2, the next Tech Talk is scheduled for May 25th. And as Shaun said, it will be the second component on space applications. So thank you all so much.
Thank you.